In the previous lecture, we were looking at how to compare acid strength by comparing pKa values or Ka values, which was called quantitative analysis. Here we're going to learn how to compare acid strength qualitatively or qualitative analysis by comparing their structures without using pKa values. So this is really useful because usually you're not going to have a Ka chart in front of you, or if you don't want to memorize every single pKa value for every possible acid, then you can use what we learn here to analyze the structure in depth and all different types of things to think about and consider to determine if something will be a better acid than another. And that's really what will drive a lot of organic reactions forward. So one thing that we'll consider is formal charge. That can have a major effect on stability, as we saw when we looked at resonance structures as well. The more effectively that a product that's formed can stabilize its formal charge, the more that equilibrium will favor that product. So if you form a product that has a formal charge that's not stabilized at all, the equilibrium is probably going to actually favor the reactants instead. So if we kind of dive in by looking at two molecules, comparing structurally hydrochloric acid, which is HCl, with butane, which one would be a stronger acid? And what you want to think about anytime you're comparing structures of acids are, what is their structure of the conjugate base? Because the more stable the conjugate base is, the stronger that acid will be. So that's always something to keep in mind, is that we are going to actually assess the stability of that conjugate base. And then that will tell us who is the stronger acid. So for something like HCl, that's a strong acid. HCl will ionize into a hydrogen ion and the chloride anion. The chloride anion is HCl's conjugate base. And what's not usually shown when we just write Cl minus that you have to know is there is 2, 4, 6, 8 lone pairs of electrons on there. So it has that -1 formal charge on it because of having 8 valence electrons. So it has a full octet. That helps contribute to its stability. And chlorine is very electronegative. So it's able to easily accommodate having those extra electrons. I'm sorry about that. My dog is annoying sometimes. So if we compare our acid-base conjugate pair here, we can see that chloride is electronegative. It has a full octet. It's able to stabilize having that extra negative charge around it. So this makes it a very stable conjugate base. And since that conjugate base is stable, that is actually why HCl is a strong acid in the first place, and not a weak acid. Now, if we compare that to an organic compound like butane, butane's line bond structure would look like that. And we're just going to assume that at the end, one of the hydrogens, now remember there's 3 coming off there, but we'll assume that we're going to lose one of the hydrogens if it's going to act as an acid. So maybe we lose the hydrogen in red. And when that happens, if we have loss of a hydrogen ion from some base maybe, what we end up forming is a carb anion, because the electrons that would be in the carbon-hydrogen bond would stay on that end carbon right there. So we have an extra set of electrons, and we have a carb anion. That carbon has 3 bonds, one to another carbon, and it still is bonded to the 2 other hydrogens that we drew. So now we want to say, how is this carb anion as a conjugate base? What is the stability like? So we said chlorine was very electronegative, which allowed it easily to accommodate having that extra negative charge. Carbon is not very electronegative. So it's not as easy for it to accommodate that negative charge or stabilize that negative charge because it's not super electronegative at all. And it does have an octet, but it's not stable because of carbon's low electronegativity when compared with many other elements on the periodic table. So in terms of acidity, that means that butane is not very acidic. And for a lot of alkanes, butane, pentane, hexane, removing a proton from an alkane is typically not very favorable because anytime you do that, the conjugate base is going to look like the one we just drew here where you have a carb anion. And so if there's nothing else on that molecule to help stabilize that carb anion, if you just have a straight normal alkane, it's usually not going to react in a way that it is an acid because it's not forming a stable conjugate base. So when we are looking at structures in order to analyze how strong of an acid something can be, the first thing you want to do is draw that conjugate base. Remove the proton and look at what does the structure of that conjugate base look like. If there is something, and we'll look at what those somethings are, that can stabilize the negative charge, that leads to it being a stronger acid. So the things that we want to consider, the factors, are the type of atom that is carrying the negative charge. So is it a chlorine? Is it a carbon? Is it a fluorine? How electronegative is that atom? How electropositive is that atom? Resonance. Is there any type of resonance that can happen? Remember, the more resonance structures you can draw for something, the more stable it is because it has more delocalization of electrons. So greater resonance equals greater stability. Something called induction, which this will be a new concept that we introduce in a little bit. And then the type of orbital where the charge would be living. So sometimes when we remove a proton, let's say we remove a proton and we have a carb anion on a carbon, but maybe the orbital that that negative charge is living in is different for a bunch of different carbon atoms. So if it's a hybrid orbital, is an atomic orbital, what is the difference between the orbitals where the charge is living? That has an impact on how stable that negative charge will be when it's left over. So the acronym that you can remember for these 4 different factors is called REO: atom, resonance, induction, and orbital. So let's start with looking at atom, so the type of atom that's going to carry the charge when we draw the conjugate base. And as we actually saw in our previous example with hydrochloric acid and butane, this is going to be really similar. More electronegative atoms are better at stabilizing a negative charge. So we're going to compare 2 compounds that could act as an acid potentially. Butane, we're just going to consider this 1 hydrogen on butane, and then an alcohol, and this is called propanol. Later we'll formally learn how to name alcohols, so don't worry about that right now. So if we remove each of the protons on our potential acids, and we draw each of their respective conjugate bases, what we're going to have for butane is, we already saw this, we're going to have an extra pair of electrons that's left over from when these electrons get sent to that carbon at the end there. And so we'll have a negative charge. And if we deprotonate propanol, we're going to have an oxygen that has a negative formal charge on it when these electrons get left on the oxygen. And remember, what's not being shown on that oxygen in the first structure of propanol, there's already 2 lone pairs there because it doesn't have a formal charge, so it must have 2 lone pairs and 2 bonding pairs. So now it has 3 lone pairs. And so now we ask ourselves, who's better able to stabilize that negative charge? Is it the carbon atom right here, or is it our oxygen atom? So we would consult the periodic table and we would know our trend for electronegativity. The general trend for electronegativity is that it increases as you go from bottom to top within a given family, and it increases from left to right as you go across a given period. So your most electronegative elements are all going to be in that upper right-hand corner of the periodic table. So we just have a truncated version of this below, but all we need to do is compare carbon to oxygen. So carbon is here, oxygen is here. Oxygen has a higher electronegativity or a greater electronegativity. And since it has a greater electronegativity than carbon, it's more able to stabilize having a negative charge than carbon would be. And so that leads propanol to being more acidic. And When we say more or less, or greater acidic or less acidity or whatnot, we're comparing the two structures that we're looking at. Propanol could be a weaker acid compared to a different organic molecule, but when we're comparing it to butane, it's more acidic because the oxygen is more electronegative. And so that means that this would be the more stable conjugate base. And this is called an alkoxide ion. Specifically, that's the propoxide ion. We're going to also look at another example looking at the type of atom that is bearing the negative charge. In our previous example with butane, where we had a negative charge on carbon, and propanol, where we had a negative charge on oxygen, those two atoms were in the same period, which is the same row of the periodic table. There's a little bit of a different trend that we're going to follow when the atoms are not in the same period, but they're in the same family, which is the same group. Because when they're in the same family, electronegativity doesn't become the overriding factor for stability. And this is actually something that we would have also discussed in general chemistry, but we'll just take it a little twist on it for organic chemistry. So as you go down a family, the size of the atoms gets larger, and that's due to filling higher orbitals. So you might recall when you're in the second period, you're filling 2s and then 2p. In the third period, 3s, 3p. Fourth period, 4s, 4p. So as you continue to go down a given family, you're increasing in orbital size, and the orbitals are getting bigger and bigger and farther away from the nucleus. So if we compare two compounds that are in the same family, we have H2S, which is a gas, and we have H2O, which is actually a liquid. And water is only a liquid due to its strong hydrogen bonding that can exist, that we don't have in stuff like H2S. But regardless, if we were to consider both of these and compare them, how they could function as acids, we're going to think about what their conjugate base would look like if we removed a proton from each of them. So always draw the structure so you can analyze the stability. So we'd have H, S, sulfur. We actually are looking at those lone pairs of electrons on this structure. If we remove a proton, the electrons will get left with sulfur that are in this covalent bond, so it'll have an extra set of electrons around it. Sulfur is in group 6A, and so it likes to have 6 electrons around it. In this structure, it has 7, so it has a negative 1 formal charge. And we can do the same thing with oxygen, or with water. So we're going to have this set of covalent electrons being left with the oxygen, and our oxygen will also have a negative 1 formal charge. So now in our conjugate bases, we have a sulfur bearing a negative charge, and we have an oxygen bearing a negative charge. And so the overall riding trend for size across the periodic table is that as we go across the periodic table, the atomic size increases as we go from top to bottom within a given family, and it increases as we go from right to left across a period. So it's actually the exact opposite trend that we saw for electronegativity. Now, really, when we're dealing with looking at the type of atom, we're only going to be looking at things that are in a given family rather than left to right, because as we saw in the previous example, when we're dealing with atoms that are in the same period, we're comparing their electronegativity, versus when we're dealing with atoms that are in the same family, we're comparing their size. So in our example here, we're comparing sulfur bearing a negative charge with oxygen bearing a negative charge, and we can see that both of these are in group 6A, and sulfur is below oxygen, so sulfur is larger. It's a larger atom. We're putting electrons in farther out orbitals. And so what that means in terms of our conjugate base is that HS minus is going to be the more stable conjugate base. OH minus, or hydroxide, is a less stable conjugate base. And so our more stable conjugate base tells us who our stronger acid is. So H2S is actually a stronger acid compared to water. Water would be a weaker acid because it has the less stable conjugate base. When you're looking at conjugate bases to compare acidity, starting with the atom is kind of the low-hanging fruit. If you can figure out who is going to be more stable just by looking at the atom alone, then you might not even have to move on to the other factors such as resonance, induction, or orbitals. But sometimes you'll have to move on to the other factors. Here we didn't have to consider anything else because looking at the type of atom gave us the answer we needed. We can also verify after the fact if we picked the stronger acid or the weaker acid by looking up pKa values for our molecules. So the pKa for H2S is equal to 7.0, whereas the pKa for H2O is equal to 15.7. So remember, a lower pKa indicated a stronger acid. And so that corresponds with what we predicted just based upon the structure. Next, we're going to look at the second factor to usually consider is, do you have any resonance? Resonance will greatly stabilize a formal charge if you have it by delocalizing it across multiple atoms. So it'll spread it out. Let's compare two organic compounds that could act as acids. The first one, ethanol, is an alcohol. Remember, the alcohol functional group is just the OH portion of it. And then acetic acid is a carboxylic acid functional group. And so what we're going to do is consider what would the conjugate base look like when a base comes and plucks the proton off of each of these. So each of these could function possibly as an acid depending upon who they are reacting with. And so we'll work over to the right of them. Acetic acid, deprotonated, would leave these electrons with the oxygen. And so we would have our carbonyl carbon. Our oxygen has 2 lone pairs, but we have an extra third one due to the electrons being left there. So it has a negative charge on the oxygen. And then with ethanol, we're going to have an ethyl group, an oxygen with at first 2 lone pairs, but then once these electrons get left with the oxygen, after it's deprotonated, we'll have a third lone pair. So it has a negative 1 formal charge as well. Now, notice in this example, our atom bearing the negative charge is the same. It's oxygen in both cases. So A for atom doesn't help us at all. So now we want to consider resonance. And that's why it's really important that you understand resonance before undertaking this. In our F oxide ion, which is our deprotonated ethanol, our negative formal charge is localized on the oxygen. There's nowhere else I can move any of those electrons to in that structure. If I was to try to move a lone pair of electrons over in between carbon and oxygen, I would exceed the octet on this carbon right here because it already has 2 bonds to hydrogen and another bond to carbon right here. So it can't accept a double bond in between that carbon. That carbon is sp3 hybridized. It's not sp2 hybridized. So I don't have any resonance structures I can draw for my ethoxide ion. Now, when comparing ethoxide to our carboxylate ion, which is what is the ion for acetic acid we have here, we can take actually one of those lone pairs of electrons that are on oxygen, we can delocalize them and move them here in between carbon and oxygen, and then that would make the pi electrons on in between our carbon and oxygen of our carbonyl bond have to shift up to the other oxygen. So this was one of our patterns of resonance that we saw. We have a lone pair that is allylic. So we're moving or delocalizing that allylic lone pair, and then we had to actually move the pi electrons of the carbonyl in order to not exceed an octet on this carbon atom right here. So if we draw a resonance arrow, our resonance structure for something like this, we have the top oxygen now with 3 lone pairs of electrons. That one now bears a negative charge. We have a double bond right here in between carbon and the other oxygen. and that other oxygen has 2 lone pairs of electrons. So it does look like it's just the molecule turned or flipped in this case because both of the atoms outside are oxygen, but it still is a valid resonance structure. It follows one of our resonance patterns. So we would say that this compound is resonance stabilized. Which, since it's resonance stabilized, that means that it's more stable. So when comparing our carboxylate ion with our ethoxide ion, we have a more stable structure for the carboxylate because it's resonance stabilized. So since that's my more stable conjugate base, that means acetic acid is going to be my stronger acid. And it's even in the name. We even actually call carboxylic acids acids because when comparing organic molecules, carboxylic acids are some of the stronger acidic organic molecules. They're not very strong when compared with inorganic mineral acids such as sulfuric acid or hydrochloric, but in terms of the organic compounds and functional groups, they are. So that would make our alcohol our less acidic compound, or our weaker acid. Just keep in mind that when we're talking about acidity, it's all relative. We're comparing the acidity of one thing with the acidity of something else. And so how acidic something is can change. And whether something's going to function as an acid or function as a base will change depending upon who it's reacting with. Next, we are going to consider induction. Sometimes when you're analyzing structures, the atom will be the same, so we can't use A. Sometimes they will both have the same resonance structure that you could draw, so we can't use R. So we would move on to I, which stands for induction. And induction allows a negative charge to spread out. It doesn't spread it out in the same way that resonance does, we'll see, but it does allow it to be spread, which stabilizes that charge. So induction, formally, the definition is the withdrawal of electron density that occurs when a bond is shared by two atoms of differing electronegativity. In order to show what induction is and how it stabilizes something, or how it can stabilize something, we're going to look at two organic compounds, acetic acid and a derivative of acetic acid, trichloroacetic acid. So if we were to consider what our conjugate bases would look like if we deprotonate each of these molecules, we would have acetic acid without its proton, and then we're going to have an extra set of electrons on that oxygen, so it has a negative formal charge. And as we just saw with acetic acid, this carboxylate, which is the acetate ion, acetate is just the name of this carboxylate ion, this guy does undergo resonance. We already drew the resonance structure for that. Now, consider the conjugate base for trichloroacetic acid. So if we deprotonate trichloroacetic acid, these electrons will stay with that oxygen there, and we're going to have 3 chloro groups coming off here. We have our carbonyl carbon. We have an oxygen that now has an extra pair of electrons, and so a negative 1 formal charge. Notice how this molecule could also have resonance. They both have the same atom bearing the negative charge, that's oxygen. They both have resonance. And so just to draw our resonance structure for the conjugate base of our trichloroacetic acid, we would take one of our lone pair of electrons, delocalize it in between carbon and oxygen, move the pi electrons of the double bond up to the oxygen. So our resonance structure would look like this. So really, we'll draw a resonance arrow as well. Really, the only difference between these two molecules is the fact that we have 3 chloro groups on the trichloroacetic acid. So how do those chloro groups impact the acidity of something like this. We know that chlorine is very electronegative. And so the definition of electronegativity is the ability of an atom in a covalent bond to pull electrons towards itself. So if we have 3 really electronegative chlorine atoms on our molecule, and they're not very far away from that negative charge that we have on the oxygen, they can pull some of that electron density away via induction. So think about this negative charge being pulled toward this chlorine, it being pulled towards this chlorine, and it being pulled towards this chlorine here. So even the number of chlorines on here will impact how much induction can occur. So these red arrows here, I'm trying to show you induction. So that tells us that because that negative charge can get pulled away slightly from the oxygen by having these electronegative chlorine atoms really close by, that this is going to be more stable. And then our acetate ion is going to be less stable when compared to our other conjugate base. So because that negative charge on that oxygen is being stabilized via induction, that means that trichloroacetic acid is going to be our stronger acid. And these are 2 examples where we have a carboxylic acid for both of them. Both of them are carboxylic acids because they both contain this functional group right here, the carbonyl next to an OH group. What's different is having those 3 chlorine atoms. And if we were to compare the pKa values, the pKa for acetic acid is 4.75, so it's fairly acidic, but the pKa for something like trichloroacetic acid is 0.70. So it's much more acidic than acetic acid, and it's all due to the induction effect of those electronegative chlorine atoms. In this example below, let's just look at how induction affects pKa. You can see that on the far left, we're starting off with our acetic acid, which is just a carboxylic acid. It has 0 chlorine atoms. And so we actually just drew the conjugate base, which was acetate of that structure. Now, when we add 1 chlorine atom here, how would this proton function as an acid? How would this molecule be an acid when it removes that proton? Notice the pKa went down 2.87 when we just have 1 chlorine atom next to it. Next, if we add 2 chlorine atoms, our pKa went down even more, 1.25. We got 2 chlorine atoms on this carboxylic acid. And then lastly, comparing that to what we just saw with trichloroacetic acid, we have 3 chlorine atoms here. Our pKa is very low, all the way down to 0.70. So that means that the ability for a base to remove that proton is going to be easier because it's such a strong acid. Its conjugate base is very stable. So with the addition of each chlorine atom, the molecule became more and more and more acidic. So that was our trend. As we went in this direction, we saw increasing acidity. The last factor that we're going to use to analyze structures is the orbital. So orbital will definitely affect the formal charge. So we want to be able to assess what orbital that formal charge is living in. If we look at this molecule, for example, imagine if we deprotonated this hydrogen on the left side versus if we removed this proton on the right side. If we have a base that comes along and grabs that proton, remember the electrons right here in this hydrogen-carbon covalent bond will stay with what's next to it. In this case, it's a carbon. And same thing here, if we had a base come along and deprotonate the right side hydrogen, these electrons right here would stay with that carbon. And so we're going to look at the structures of what this would look like for these conjugate bases in a second on the right-hand side. But basically, we're going to have 2 carbon atoms that have a carb anion. They're both going to have a negative charge. So the atom will be the same. We don't have any resonance we can draw. There's no induction taking place. So the last thing we can do is analyze what type of orbital that negative charge is going to live in. If we have a base deprotonate, the hydrogen that was on the left, we're left with a negative charge and an extra pair of electrons on a carbon atom that is double bonded to another carbon atom. So when you have a carbon that has a double bond on it, we want to think about what is the hybridization of that carbon. This carbon is going to be sp2 hybridized. So it's trigonal planar. Versus what is the hybridization of carbon when we deprotonated, or before we even deprotonated, the hydrogen on the right-hand side. So that would be the other molecule that we're seeing. We have a carbon-carbon triple bond here, and our extra pair of electrons is sitting in a hybrid orbital. And when carbon was bonded with a triple bond, it had sp hybridization. And so it was linear, which is why it was important that we showed a triple bond like this being 180 degrees apart. So now we're comparing the orbital. It's either going to be more stable in an sp2 hybrid orbital, or it's going to be more stable in an sp hybrid orbital. The stability of the hybrid orbital will be determined by how much s character it has. The greater the amount of s character, the closer it is to the nucleus, the closer that orbital is to the nucleus. And by having that negative charge held closer to the positive nucleus, that's good. That helps stabilize that negative charge by being close to that. So let's consider the percent S character for an sp2 hybrid orbital. In an sp2 hybrid orbital, it's about 33% S character. In an sp hybrid orbital, the percentage S character is 50%. It's 50% S, 50% P. So in an sp hybrid orbital, there's a greater percent S character. Having that greater percentage of S character allows this negative charge on that carb anion to be closer to the nucleus and more stable. So this is our more stable conjugate base. Having the negative charge on an sp2 hybrid orbital isn't bad, but when we're comparing the two, this is our less stable conjugate base. And so then that tells us, when we're looking at the structure, that the proton attached to the triple bond is more acidic than the proton attached to the double bond. So we had our carbon-carbon double bond, our carbon-carbon triple bond. There's technically two hydrogens coming off of the double bond. This proton right here is more acidic because it led to a more stable conjugate base. So an alkyne will easily be deprotonated because that proton is an okay acid, versus an alkene. Sometimes you can deprotonate an alkene as well. Those protons can, in theory, function as acids, but you would need a stronger base for that to happen. The three major hybrid orbitals that you will see in organic chemistry are sp3, sp2, and sp. So if we rank the ability of these orbitals to stabilize electrons based upon their percent S character, what's going to be our ranking? sp3 hybrid orbitals are about 25% S character. The other 75% is P character. sp2 hybrid orbitals are about 33% S character. And sp hybrid orbitals are about 50% S character, half and half. So we can see how, even just looking at the picture of these types of orbitals, that the sp hybrid orbitals are more spherical and they look a little bit more like an S orbital, whereas the sp3 hybrid orbitals are more p orbital-like. They're more dumbbell-like. So for our ranking, what we're going to see is that sp is the most stable. It's going to lead to something being a stronger acid. sp2 then, and then sp3 is the least stable. Now, just to wrap this up, the section covering orbitals, let's compare the acidity of the compounds below and their conjugate bases. How does the type of orbital play a role? So we have an alkane, we have ethane, and we're actually given the pKa values too, so we can compare what we're seeing structurally. We have ethane, and then we have ethylene. Ethylene is an alkene. And notice both of them have 2 carbons. So this one's fully saturated, the alkane. It has the maximum number of hydrogens. Ethylene, or ethene, is unsaturated. It has 1 degree of unsaturation where it has a double bond. And then acetylene is an alkyne. And we have a carbon-carbon triple bond. And that actually represents 2 degrees of unsaturation. And now if we look at what the conjugate bases of these would be. So we're imagining that we lose a proton in each one of these molecules. So for ethane, we would have 2 hydrogens coming off here, and we would have a negative formal charge because we have an extra lone pair of electrons on our carbon. In ethylene, we're going to have an extra pair of electrons there and a negative formal charge. And then in acetylene, our extra electrons and our negative formal charge. So all of these are our conjugate bases of the molecules up there. And where's that negative charge living? In what type of orbital? Because it's in carbon, it's on a carbon atom for all of them. There's no resonance I can draw for any of them. There isn't any other electronegative atoms causing induction. So now we have to use the orbital in order to analyze the acidity. The negative charge here on carbon in ethane is on an sp3 hybrid orbital. For ethylene, the negative charge is living in an sp2 hybrid orbital. And for the acetylide anion, which comes from acetylene, the negative charge is living in an sp hybrid orbital. So we can see that acetylene is the most acidic because its hybrid orbital is sp, and that can stabilize the negative charge of the conjugate base the best. It also has the highest pKa, 25, which honestly, a pKa of 25 isn't even super acidic, but remember, it's all relative. Next, in the middle of the road, we would have ethylene, and then the least acidic would be ethane, a simple alkane, because that negative charge is not stabilized really at all inside of an sp3 hybrid orbital. So it's really, really, really hard to deprotonate something like a alkane to remove a proton with a different base. You need something that's a really, really, really strong base if you're going to remove that proton. And the pKa is 50. So it's a very bad acid in general. Let's do an example. Rank the labeled hydrogen atoms. We have HA, HB, and HC in order of increasing pKa value. So we want to think about, what does increasing pKa value mean? If the pKa is getting greater, it's getting more basic. So we're going from most acidic to most basic when we rank these. So let's redraw our structure and remove HA, HC, and HB, and then we can compare what the conjugate base would look like for this one molecule. So we have a benzene ring, we have an oxygen that's going to have a negative formal charge there. We have a double bond between carbon and nitrogen. That nitrogen has 1 lone pair of electrons that's not being shown right now. So now it's going to have 2 lone pairs of electrons, and it's going to have a negative formal charge. And then down here we have an amine. We have a methyl group coming off of the nitrogen. And we also have now 2 lone pairs of electrons. Our oxygen has 3 lone pairs not being shown. So we're left with oxygen with a negative formal charge, nitrogen with a negative formal charge in HC and HB when we removed them. So the first thing we should look at is the type of atom. Start with the low-hanging fruit. Between nitrogen and oxygen, oxygen has the greater electronegativity. So therefore, it's going to be able to stabilize the negative charge better. And since they're in the same row of the periodic table, row number 2, we're going to use electronegativity as our trend, not size. So right away, we can say that HA is going to be number 1. That's going to be our most acidic proton on this molecule, just due to the type of atom that negative charge is, the atom that is bearing that negative charge, which is oxygen. Now we can compare HB and HC. They're both on nitrogen, so I can't use the atom in order to analyze these two. So the next thing I would check is there any resonance that can be drawn? In HB, notice that one of these lone pair of electrons on nitrogen, they're allylic to this double bond right here. So they could resonate in between carbon and nitrogen, but then technically our carbon here would have too many bonds, so then that's the point of them being allylic. The pi electrons could resonate to this carbon right here. We needed 2 curvy arrows to draw that resonance structure. So HB has resonance. And remember, that's stabilizing, so that's going to make it more acidic. Does HC have resonance is the question now. Can I take any of the lone pair of electrons on the upper nitrogen and move them anywhere? There's already a double bond in between carbon and nitrogen there. I can't push another bond in between that carbon and that nitrogen. So that would be a bad arrow I just drew. I can't do that. I have nowhere else I can move those electrons to. And nitrogen would have greater than an octet if I did that. So I can't exceed an octet on a second period element. That was one of our rules. So in this case, HC has no resonance. So that means that HB is going to be the next acidic, that'll be number 2, and HC will be number 3. So for our ranking then, most acidic to most basic, we're going to have HA, which had the most stable conjugate base, followed by HB, that was our next stable conjugate base, nitrogen and resonance. Our least stable conjugate base in this group was HC, which was on nitrogen, but it had no resonance. So that would be our ranking. Let's try another example using REO, atom, resonance, induction, and orbital. In order to rank the following by looking at their structures, we're going to rank them in order of increasing strength. So we're first going to draw the conjugate base for all of these by removing the proton that would be acidic. And every time you have a base remove a proton from a would-be acid, those lone pair of electrons stay with the atom that they're bonded to in that covalent bond, because a base just removes a proton, which is just a hydrogen ion with no electrons with it. So we have our conjugate bases that we're going to draw. We have oxygen, and it's going to have 2 lone pairs of electrons on it. Notice the oxygen had a positive formal charge in A, and so what's not being shown is that there was 1 lone pair of electrons there. Well, now oxygen has 2 lone pairs of electrons and 2 bonds to it. It's divalent, so it's neutral now. It doesn't have a negative charge. It had a positive charge and it went to neutral. Same thing with the rest of these. When we remove our proton here, we're going to have a conjugate base that looks like that. It's an ether for B. And in A, that functional group would be what? We have hydrogen here that's not being shown. This would be an aldehyde. For C, if we deprotonate, we're going to be left with nitrogen with a lone pair of electrons bonded to 3 methyl groups. This is an amine. For D, we're going to be left with oxygen. There's a double bond on the other side. It's not directly bonded to the oxygen, but it's next to it. There's going to be 2 lone pairs of electrons on our oxygen. This is another example of an ether. E, we're going to be left with nitrogen that has 2 methyl groups coming off, and then a carbon that's bonded to 3 highly electronegative fluoro groups. Notice fluorine is the most electronegative element on the periodic table. And so this is another amine in terms of the functional group. Okay, so when comparing our conjugate bases that are all down below, we want to start with what atom we have that extra pair of electrons on when we removed the proton. So kind of the first thing to check is A for atom. So between oxygen and nitrogen, we know that oxygen is more electronegative than nitrogen. So that's going to lead to a more stable conjugate base. So right away, we can start by comparing A, B, and D, because we know that A, B, and D are going to be more acidic than C and E will be, because C and E have that extra pair of electrons on a nitrogen versus on an oxygen. So then looking at A, B, and D, everything's on an oxygen now. So now we want to consider, is there any resonance? In A, there is no resonance. In B, there's no resonance. But in D, we can see that we have an allylic lone pair. So we can take that lone pair of electrons and push that in between oxygen and carbon, and then the pi electrons could move to the carbon on the end. So we do have resonance in D, and our resonance structure would look like this. We would now have a positive charge, positive formal charge on that oxygen. Let me draw that a little bit better there. The lone pair of electrons on the carbon at the end. So we do have resonance for structure D. So that's going to tell us that this is going to be the most acidic. We can call this one number 1 right now. Now between A and B are other oxygen-containing structures. We want to look at the original structure and think about what is the hybridization of oxygen, because there's no induction going on. There's no other electronegative atoms that are bonded anywhere within those. So we're going to jump down to looking at the type of orbital that the electrons would occupy. So oxygen, it has a bond here, it has a bond here, and it has a lone pair of electrons. This is AX2E. AX2E is derived from AX3, which is the trigonal-planar family, which everything in the trigonal-planar family has sp2 hybridization. In our B structure, remember there's a lone pair of electrons here on that oxygen, which is why it has a +1 formal charge. This is going to be AX3E. AX3E is from the AX4 family, the tetrahedral family, which is going to be sp3 hybridized. So just as we saw before, sp2 hybridization is better than sp3 hybridization because it has a greater character of S. So now for our ranking here, we're going to give A ranking number 2 as the next strongest acid, and then our ether number 3, due to it being sp3 hybridized. So moving on now to compare structures C and E, our amines. We have in structure C no resonance or anything that can occur. We have no induction. And they're both going to be occupying the exact same type of orbital. They're the same functional group. They're both amines. But in structure E, we have a lot of induction that can take place. We have 3 fluoro groups that are highly electronegative that are going to pull that electron density that is localized on the amine towards them, though. It's not a resonance structure. It's just pulling it via induction. So it's essentially allowing that negative charge to be spread out a little bit, or the lone pair of electrons. It's not a negative charge this time. They're just a lone pair. So that means that E is going to be more acidic than C. So we'll give E number 4. And lastly, our amine C number 5. And actually, amines are usually bases. These are protonated amines that we're starting with, and protonated oxygens. So that's why when we removed the proton to draw the conjugate base, we didn't have any negative formal charge. All of these molecules were neutral because we started with a +1 formal charge. So that's going to be how you want to break down using REO to analyze different structures to determine their acidity. So our ranking here then, our ranking of our structures would be, we had D, or our least acidic would have been our number 5. So C, we're rating them increasing strength, and then E, and then B, A, and then D was the most acidic.